Hey, what's going on, folks? It's Mike here, and welcome to the next lesson in our D programming language series. Today, we're going to be talking about another way to create a custom data structure known as a union. Now, previously in this series, we've been looking at things like structs, tuples, variants, which are a type of tagged union. So we have seen these briefly, but let me go ahead and talk about what a pure union is. And again, if you're coming from a C or C++ background, this is going to be quite familiar. So let's go ahead and dive into it. Now, this is actually going to be part of the built-in language. So let's go ahead and zoom in here, take a look at our language reference, and we're going to go ahead and see structs and unions. Now, if you've been following this series because you've been subscribed, you'll notice that we have been to this page many times to talk about structs, but we haven't talked yet about unions. So let's go ahead and take a look at unions here and find where they are here. So I'm just going to do a quick search for union. And what we're actually going to find is unions have a lot of power. Again, if you're coming from a C background, basically they're just a way to hold some data, which we'll get into. But we can have other things like constructors and things that we've learned about structs or otherwise. So let's go ahead and just look at, say, union members here and find an example of a union here. Here we are. So here is a union, which we'll look at here. And basically, the difference between a struct and a union is defined here. I'll go ahead and zoom in on it a little bit here so we can read it. And it says a struct can contain multiple fields. Okay, so we've looked at structs, for instance, like one here that has an integer or maybe several of these here. But the difference is, well, a struct has multiple fields which are stored sequentially in the data. A union uses overlapping storage. So what exactly does this mean here if I have something like this here, for instance? So let's go ahead and just lay this out here. So here on the left side, I'm going to draw what we've learned about, which is a struct, where I might have, say, an int x here, and let's give it a name here, like we have a point, for instance, in an int y. And these would take, say, 4 bytes of data. 4 bytes, 4 bytes. A union, on the other hand, if I draw it like this, if I have an int x here, which is 4 bytes, and if I wanted to create another y here, well, notice I'm not going to draw a line between these here. They're occupying the same space here. In fact, a better way to lay this out is how memory is laid out, sort of horizontally here, for our union type here. I'm going to go ahead and label it down here, union, where I might have, again, little boxes here representing 1 byte of information. And I might have an int here that takes, say, 4 bytes. So let's go ahead and just label it there. And maybe I'll have a character here that just represents 1 byte. And maybe another type here. And you can see how this is getting a little bit messy, but I'll just draw in a long here, which takes 8 bytes here. Let me make sure I get 8 bytes. So you'll see that the memory overlaps here. And I'll actually, let's get rid of these 2 boxes here. Here, let me just scratch them out here quickly. But the basic idea there is, oh, here, we can actually delete here, is that our union here takes up the amount of space as the biggest data type here, this long here, okay, which I'm highlighting. And what that means is that, well, if I have a long here for the data type here, let's go ahead and just put in some number here, and I'd access this with union, and then whatever the long's name is, I'm just going to label it long, equals some value like, 8 billion, some really large number here that can be stored in a long. Let's do 8 million here. It's going to fill in as many bytes as it needs. But if we access this union as an integer here, so if I come down here to int union.int, well, the memory that's currently occupying it is 8 million. So if I'm just accessing this, and maybe it's not big enough for this data structure, or as a better example, if I do int char, it's just going to use, whatever the last bits are and pick out that data. Okay, so hopefully that makes sense illustrating it. Let's go ahead and take a look at some code here, and then we'll talk about a pragmatic example where we might want to actually use this. So again, let's go ahead and look at a union here, lowercase here. I'm just going to call it U. And let's go ahead and give it a integer here just to start here. So one field here. And let's just go ahead and create an instance of it. I'm going to use underscore, or sorry, lowercase u here. And we can actually use like the structs, a struct literal, and I can actually initialize this to something. And let's just go ahead and write out the value here. Okay, let's go ahead and start this out here. And let's see here if I made any mistakes. Oops, one mistake here. My C++ here. Let's go ahead and assign it here. There we are. And I've got this union here. And it's writing out, this is kind of strange here, the uppercase U character. Well, let's try to debug that a little bit here. Let's go ahead and give this a name. I'm just going to call it my union here. Okay, because I think this will be a mistake that you also make as well. And let's go ahead and run this here. And it's just printing out the data type. Okay, so my union, if I'm just printing out what this is here, which is kind of neat here. What we probably want to do is just access the field here. And we can see that it's running 5. Okay, so this looks pretty normal here. In fact, if I go ahead and change this here to a struct, we're going to get exactly the same program here. Okay, so nothing different. So again, the difference with a union is when I add in multiple types, and in particular, different types here. So let's go ahead and just use a character, for instance, A here. And I'll kind of arrange these here. I usually like to put the smallest type first here. Let's go ahead and run this, and it works. But let's go ahead and now try to access our union with A here for the character. Okay. If I go ahead and run this, I get 5 and then a space here. Okay. Well, maybe I didn't initialize this. Okay. What else could be going on? Let's try a different value to illustrate this. 50 here. Okay. And I get a 50 and then I get a 2 printed out here. Okay, that's curious here. Let's try some other values. 64. And I get a 64 and an @ sign. That's curious. Let's increment this a little bit here. Maybe you'll see what I'm doing here. And I get an H. Well, I'm pretty sure when I initialize a character, the initial value isn't H. Okay, nor was it the @ symbol, and so on. So again, what this is doing, if we go back to our illustration here, our little scribble, is it's looking at, whatever these bytes are that are filled in with the value of 72. That's what we've written out here. And then it just happens to be that 72 is the ASCII character for uppercase H here. Okay, so again, let's go ahead and prove that this is using overlapping storage here. So if I go ahead and access one of the properties here for our union, and let's go ahead and do the size of for our data structure, you'll see that it's 4 bytes, which an integer is 4 bytes. A character is 1 byte, so we would think that this should be at least 5, but no. Again, a union sizes itself to the largest data type of all of its fields here, okay? Versus if we do this experiment with, say, our struct here, if we change it back here, you'll see that we get 0 here for our value, for our union here. You'll see that it is using the struct literal, so it's able to take in 72 as the character and initialize it to H. That's why we got a 0 here. And then the size of our data structure is 8 bytes, okay? Because we have 1 bit here, it pads it 3 additional bits, and then 4 bytes here for our int. Okay, so actually I should rearrange these to try to be more efficient. Okay, as such, I mean, it's still going to be 8 here, but we could turn off the padding or pack it like we've learned with smaller values. But this time, again, you'll notice we have 72, an empty character here, and 8. And let's go ahead and go back to our union. And I'll run it so you can see the difference here. This time I get a 72, I get my H, and so on. Okay, so that's the idea with the union. We get overlapping storage, and it can be a really compact way, though, to represent lots of data. So what's a use case where we want to actually use a union versus a struct and having all the data? Because it seems like it would be a disadvantage. But the trade-off is, again, that we're able to have a very compact data structure. I'll go ahead and show you from one of my favorite APIs, SDL, which is Game Programming Framework. You can see my series on my YouTube channel. And here's an example of an event type here. So imagine if you're clicking your mouse, moving your keyboard, pressing buttons. Maybe you have a joystick. Maybe if you have a touch sensor on a stylus, or maybe if you're on an iPad or something. The idea is you want to be able to capture all these events. But you can imagine a structure that has all these unique events would go very large. In fact, how large would it be? Well, it would be this large here. And even if all these fields were just, say, 1 byte, this is still a lot of information, when maybe we can just compactly store what actually happened in 4 bytes, for instance. And that's what these types are defined as here, which I believe they're all uint32s, although I could be wrong here. But basically, depending on what event occurred, maybe it was a display thing, a window event, or a keyboard event, and we can dive into it here, we just figure out based off of the type of event what the rest of the data or the bits mean. And that's the idea with a union. We're able to sort of change representation on the fly and do this in a really compact and powerful way. So that's the idea with unions, folks, and they have lots of really nice ways to work, especially in event-driven systems. So if you're developing like games or applications that users work with, again, it's just a really optimal way to work with your data. All right, folks, so with that said, that's unions. We've now learned about them, and you now know the difference between structs if you didn't already, and there's a few neat things in the deprogramming language like the union literals. Again, you can track your progress on my website if you want to keep track of all these things, structs versus unions versus variants, and so on. You can go ahead and sign up and follow on the series. And I hope you enjoyed this lesson. If you have other questions about unions, we are going to look at them again later on in the series, so make sure you don't miss those. We'll talk about anonymous structs, anonymous unions, and these types of things, which are just other common sort of paradigms to use with this different tool here. All right, folks, with that said, hope you enjoyed this lesson, and I'll look forward to seeing you in the next one.